Okay, so in this video clip, we're going to take a look at intelligent lattice search. This is a technique that is now established in the literature. I'll leave two references here. First one is to the Journal of Derivatives, this paper, American Option Pricing and Accelerated Lattice Model with Intelligent Lattice Search. And the second paper, if you follow the link, the collab, I will put underneath the video clip and the link is embedded. But the second paper here is from the Journal of Futures Markets. And again, we set up the acceleration technique, not for necessarily just Cox-Ross-Rubinstein, but here in particular Lyson, Reimer, and Tian binomial models. Now, the key point is we're trying to look at the performance of intelligent lattice search relative to peers. So we're going to look at different architectures, different structures on the binomial lattice and compare the fast executing code against slower code, and then where we use static memory, where the typically for in textbooks, when you're explaining to students how the binomial model works, we take all the nodes as a single chunk of data, and we try to process that bigger uh, amount of data at one go. It's quite inefficient. And then we then deploy the second snippet of code that we'll use here is based on Espen-Hague, which makes use of dynamic memory, where at each step of the tree, we sequentially pass the values from the preceding step across. That is a lot more efficient. And then the third snippet of code that we use here is we apply the Espen-Hague dynamic memory. This idea of the dynamic memory is broadly available in the literature, but the one that people typically can read, you will find from Espen-Hague. I'll leave a link under the video clip to Espen-Hague's textbook. The third snippet of code we'll use here again employs dynamic memory, but also truncates the zero region of the tree. And then the fourth code is intelligent lattice search. It's based on intelligent lattice search, and it aggressively prunes the tree so that the non-relevant, non-essential nodes in the tree are discarded, and that speeds up computation. Again, to see how that actually can work, if you're going to take a deep dive here, I recommend taking a look at this playlist where using VBA code in Excel, you can observe directly the speed improvement, but also there is a good overview in terms of how the tree operates. The lattice, Cox-Ross-Rubinstein lattice works, developed here in the video clip. Okay, so in terms of a speed and performance, then I'll go down first of all to the first tree, the Cox-Ross-Rubinstein lattice. And note here, if I go into the content folder in our Google Colab here, we don't have any data except sample data. But when we execute this file, write file CRR static, it tends to come in to our content folder. Let's just go to the content folder and refresh. Okay, and now we can see it's come across. And if we double click, all that's basically happened is we saved across, so that the directory where our code gets saved is here. And then we execute using a bash command, and we get the output from our model executing. And note here, the parameter values are the same as those given from Broad to Temple, except I've lowered the step size from 15,000 down to 1,000 just for benchmarking purposes. And when we go down to our model and observe the speed it's taken to execute the code, it's 0.0825 seconds. Okay. Again, the value we get here is comparable to the value that we observed here from the Cox-Ross-Rubinstein tree from Broad to Temple, 1996. Okay, using the same parameter inputs. Now, we can use a level tree optimization, and this was a suggestion from Nicholas Cantarutti. And he noticed that in some code that I shared with him, that if we use the G++ wall level tree, we can improve the estimation that we get the same estimate for the value of the option, no question there, but we do improve the speed performance of our C++ code, just executes a lot more efficiently. So there's a small bump up here we can directly observe in terms of using the level tree optimization. Okay, next snippet then based broadly on Espenhogue design. And when we use dynamic memory and execute our code, the value of the option, same as before, but we have improved our speed performance quite substantially. So now it's 0.04 seconds for the 1000 step tree. That's quite fast. And again, we note using the level tree optimization, when we look at the performance of our model, we do get a speed improvement again using the level tree optimization. Again, the value of the option for the 1000 step tree is the same. So we're using, as before, the same parameters that as identified by Brody to Temple. Okay. Third snippet of code, we are using dynamic memory and we're truncating the zero region. So most options will have a zero region. When we look at the valuation, most option binomial trees that estimate the value of an option will have a zero region within the tree. And when we execute this code, we're finding that we get a speed improvement again, same value of the option, using a level tree optimization in Google Colab. We have the speed now is 0.02 seconds. Let's just run it again. There is a little bit of variation when we run these. So possibly to make build-in resilience here, we should probably have estimated a book of options, but it varies between 2 and 3. 0.2 and 0.02 seconds, 0.03. And likewise here, some variability, 0.04 seconds, 0.03. Okay, so we can see a small improvement using the level tree optimization. The final snippet of code we have here is based on intelligent lattice search. And again, the same parameter values as before. If we go into our content folder, you'll note here if we refresh, all that code is being loaded across. We execute using the bash command, which is unoptimized. And you can see a fairly significant, quite a dramatic improvement here in terms of speed performance. But when we use the level tree optimization, it's a vast improvement. So intelligent lattice search running in C++ with a level tree optimization, so where we use the G++ wall level tree optimization, you can see the significant improvement there. In fact, if we to get a sense of the magnitude there, if we just take the ratio of those two values, Control C, we'll be able to get a sense of the improvement across. So let's run that. So it's about almost 4 times faster using uh, the level 3 optimization. Okay, now to summarize, I put together this table before running the evaluation for static memory, dynamic memory. Maybe I can zoom out here to get the entire window. Yeah, so we have our static memory, dynamic memory with truncation, and intelligent lattice search. Using the bash command, right? In terms of milliseconds, or yeah, it's probably easier to describe in milliseconds, 78 milliseconds for static memory, 47 milliseconds for dynamic memory, 46 for dynamic memory with the truncated region, 1.5 milliseconds using intelligent lattice search to run the 1000 step tree. But when we execute using a level 3 optimization, uh, the, the speed improvement is a multiple of possibly 4 here, and has a fairly significant, a very dramatic improvement compared to the others. So if we look at the 78 relative to the 52, a bit of an improvement, some improvement, maybe a doubling, but here it looks like more quadrupling in terms of speed performance. Uh, in each instance, intelligent lattice search uh, very significantly improves the performance of the tree. Okay. Um, I'll leave more detail here in terms of the optimization. In terms of why use the different techniques, for the static technique, I would recommend it for teaching. For looking at how you can speed up the static um, implementation, I would use the dynamic memory as outlined by Espen Hogue. Truncating the zero region will bump up a small amount the performance of your tree, and then intelligent lattice search is by far the most fast executing code. Again, with the same level of accuracy guaranteed no sacrifice in terms of the level of accuracy of your tree. Okay, this collab I leave underneath the video clip, and you'll be able to access and implement the code um, on your own machine. Let's leave it there.